Hello and welcome to Physical Geology, Geology 1008. This is our introduction to geology at Illinois Valley Community College. A little bit about me. Um, I am Mike Phillips. This is my contact information. I have a master's degree in geology from Southern Illinois University at Carbondale. You can find a little bit more information about that if you go to my website. So you'll find a whole bunch of information. If you follow my courses or information about me, my office hours are there. The other way to find out most of this information is to just go through the class Blackboard. So either way works. The class Blackboard actually frames my website. And so once you click through and are kind of into the website, you can click around and find more information about me. So we'll get straight to the topic at hand, which is this course. And what is geology? What is physical geology? What is this class all about? So we'll begin with just geology in general. It's the scientific study of the earth and its processes. And as we go through these slides, we'll take kind of a brief look at how geology approaches the study of the earth. To be a little more specific, we study the physical earth, which is what this class is about. We will be looking at the composition, so that would be rocks and minerals and the materials that the earth is made of. And we'll also look at the processes that shape the physical earth. So that's really the core of what this course is all about. This information can then be taken and used to develop an understanding of what the earth was like in the past. And so we will talk a little bit about this as well, because it's very difficult to look at physical features on the earth and not think about their history, because their history will tell you about the processes that created them, and vice versa. So there's a lot of mixing in here. But we do have a specific class that we teach in the spring called Historical Geology, where we really focus in on how we interpret the Earth's past and what kind of things have happened in the course of the Earth's history. The other thing we can do with our information, our understanding of geology, is we can look at the interactions between humans and the Earth. And those interactions go both ways. So humans act on the Earth, and Earth processes impact humans. And so that is really the subject and the focus of the other geology class I'm teaching this semester, which is environmental geology, and another course I teach which focuses in specifically on hazardous processes, and that's called natural disasters. So how do we do this? Well, a geologist might be walking through Starved Rock State Park. They might walk up LaSalle Canyon and see this. In fact, you may have done this yourself. A geologist would see this and potentially have a lot of questions. Those questions might be based on what the geologist is focused on studying. So in the sciences, we tend to chop things up and study them in little pieces. So as you're looking at this picture, you might be focused on the water. So you might be thinking about what role does the water play in the creation of this scene? Is the water drinkable? Where did the water come from? Where does it go? There are a lot of questions you could ask about the water. You might look at the rocks. You might say, what kind of rocks are those? What are they made of? How did that material get there? How did that turn into a rock? And so on. So depending on kind of what your focus is, what area you're especially interested in geology, there are a whole bunch of questions that we could ask about this particular scene. Another example might be this picture. This picture was taken during a hike I took along the I&M Canal. It's at a place called Split Rock, which is not too far from LaSalle Speedway. It's just south of LaSalle Speedway, but it's along the Illinois Valley. And again, geologists would have a lot of potential questions about this. Why is there this opening? Is it man-made? Was it natural? Again, what kind of rocks are those? How did they form? How did they get there? You might notice that there's some layering in the rock and that it tilts to the left. So you might wonder, well, how did that happen? Were the layers originally flat and then later tilted? And what kind of processes would result in that tilting? This is a picture I took out in Washington State a few years ago. You'll notice it's a big pile of snow, and if you want to know how big that pile of snow is, you'll notice that kind of at the base of the snow there are some little vertical lines. Those are people. So for scale, that's just a huge pile of snow. Uh, Again, lots of potential questions here. Where does the snow come from? How does it end up in a pile there? How is it that there is still snow here? This picture was taken in October, so that's last year's snow potentially that has lasted almost the entire year, and it will probably get snowed on in the coming fall. You might also wonder why there are caves in the snow. You might notice the waterfall in the background. Again, somebody might ask about what kind of rocks are those. So lots of potential questions. We might come back to our area. So this is an aerial photo of Illinois Valley Community College. You'll notice in the background is the Illinois River. We might want to ask ourselves, how does the river work? What's it doing? How much water is going through there? How much sediment is going through there? Why is the farm field on the left-hand side of the photo? Why is that flooded? Why is that covered with water? So again, lots and lots of potential questions here. And that's really what science is about. It's about asking a lot of questions and then going out after you have all these questions and start working through an investigation. So you make your observation. In this case, it's gasoline in the groundwater. And then you have some questions. Like we brought up many questions in those previous photos. In this case, we could be more focused. The question they put up is this from the buried tank? We could be more general. We could say just where is the contamination coming from? And the tank might be one possible explanation. So the possible explanations that we have are what we call hypotheses. They spring from and kind of work with our questions. So if our question is where did the leak come from, we might say, hey, buried tank somewhere else. Now we got to do the homework. We've got to figure out what works in order to answer our question. So in this case, some proposed explanations they have or hypotheses are from the tank and from somewhere else. And we might have some other places that we're targeting. And so then what do? Well, we test these explanations. So it's good to have multiple explanations proposed because that gives you a lot of possible things to test. It kind of opens your eyes and opens your horizons to testing. So for each explanation, you could have some different things to investigate. In this case, you might test the tank for a leak. You might also test the materials that are in the tank and see if that's what's actually coming out in the well. So what kind of material is this? You might check the direction of groundwater flow. In this case, the assumption is that it's flowing from under the tank to the well, but maybe it's flowing in the opposite direction. So if we were in class, we would spend a whole class session kind of exploring this idea. And we might do that in one of our Zoom meetings as well. But the general idea here is that in the scientific process, the more possible explanations or hypotheses we can toss out, the more ideas we get for testing very broadly and comprehensively. Ultimately, our goal is to use that information that we collect to test our hypotheses and see which ones are correct and which ones aren't. And the ones that don't make the cut, the ones that don't pass the test, get thrown away. So in this case, if there's no leak in the tank and it's the wrong kind of gasoline, then we can rule out the tank and we have to start looking elsewhere. So that kind of brings up this whole question of data that we were collecting in the previous thing. What kind of data are we collecting? Well, usually when people think of data, they think of numerical data, which is quantitative data. That's what's on the right-hand side of this slide. But in geology, we spend a lot of time with qualitative data. It's descriptive data that's conveyed with words, sketches. It might be things on maps, but maybe there aren't any solid numbers attached to it. And so we have to be comfortable working with this qualitative, non-numerical data. We also do use numerical data. One of the reasons we like that is because very often we feel it's a little bit more difficult to kind of mess around and become confused. If I say the temperature is 20 degrees Fahrenheit, you know that that's below freezing and it's pretty cold. If I just say it's cold out, you don't know how cold it is. So having a number, very often people kind of privilege that. But as I said, in geology, we'll see that very oftentimes a number is pretty difficult to assign. So we want to be comfortable working with qualitative data. And we also want to think about our viewpoint. If we look at that image up at the top, there are a lot of things going on, just as there were in the pictures that we looked at. And so very often a geologist will narrow down their viewpoint and focus on a certain aspect and just ask questions about one aspect of a landscape or of a problem or of the earth. So you can see in this case, they might be looking for petroleum, they might be looking at groundwater flow, earthquake hazards. I would point out the river because I've been studying superficial processes since graduate school. So there are a lot of potential things that we could look at here. One of the questions that's posed in your book toward the end of chapter 2 is what formed this crater. And you'll see that this is also a question for your exam. And so the last part of the exam is kind of an in-depth examination of how a crater might form. And it asks you to hypothesize, propose some different ideas of how the crater might form. In this case, we can observe the rocks in the rim of the crater, and we might find little pieces of, we find angular blocks of fractured rock. We might look around the edge of the crater. We see that it's pried up some sedimentary rock layers. And we might propose a couple ideas. Maybe it was formed by a volcanic explosion. Maybe a salt deposit underneath. It turns out that salt deposits can flow when they're under pressure. Maybe that came up to the surface and got eroded away. Maybe it got hit by a meteor. So we can look for different possibilities and then examine the evidence. In the case of meteor crater, or this particular crater we're looking at in Arizona, there are meteorites found around the edge of the crater. And so that tells us that probably the meteorite impact is the most likely explanation. But we could look for salt under the dome. We could look for lava particles around just to see what makes the most sense. And so that's what you're going to do when you do that question in the exam. So there's a few more examples in the slides here. One is taking a look at the Black Hills, which is very interesting. We'll actually look at the Black Hills toward the end of the semester, in the second half of the semester, in one of our lab exercises. So some questions that I would like you to be thinking about as we go through this week in the semester are, how does science work? What makes science so special? And also, I want you to have a few goals for the class as we go forward. So what do you hope to gain out of this class? And so that's really the two topics for this week, is kind of how science works and what you would like to get out of this class. And we will meet in Zoom, we'll be in Blackboard, and we'll be in the lab as well. So I will see you as the week continues.